In this video, we're going to be talking about the learning target test for writing exponential equations. So this was our first attempt, and we'll just go over it right here. In the first problem, there is a description about a population of rabbits. So a population of 2 rabbits is doubling every year. So the context is we're starting with 2 rabbits, and each year that's doubling. We're trying to calculate how many rabbits will there be at the end of year 6. So first, we want to think about what it means for something to double. So we know doubling is multiplying by 2, right? It's twice as much. So if we start with this table, we can start by filling in 2 here. Double 2 is 4. Double 4 is 8, 16, 32, 64, and 128. So again, with exponentials, we're multiplying, make this more of a star shape, we're multiplying the output each time by the multiplier, which in our case is 2, to get the next output. When we go to write our equation, we're going to do so in this form of a b to the x, where a is the starting value, b is what we call the multiplier, or you might call it the growth factor, and then x is the input, which in our case would be years. So pause the video now, see if you can write the equation for this given the table that we've just constructed, and check in after you've given that equation a try to check your work. All right, so the equation that I wrote was 2 times 2 to the x, where this 2 out in front comes from the starting value. We start with the starting value. The 2 in the parentheses is the multiplier, and that comes from what we're multiplying each time. So I'll just highlight this as well. So 2 starting value, 2 multiplier, and then the x is the input, or the number of years. Once you have this table, we would just go to our graph and we would plot these points. So we have 0, 2, oops, change this. 2, 1, 4, 2, 8, 3, 16, 4, 32. As you can see, that doesn't really fit. I could connect these points like so. Because we're talking about a population of rabbits and time in terms of years, it doesn't really make sense for us to be talking about negative years. So I'm just going to fill in for our model the positive years. The second problem is similar. We're still trying to write a rule for our exponential relation, but we're given different pieces of information. So we have a table that we're starting with, and we have to find the multiplier. Remember again, our general form is ab to the x, where a is the starting value, b is the multiplier, and x is the timer input. So we know the starting value, right? That's 50. And now we just need to figure out the multiplier. So let me zoom in on this. In other words, 50 times this little stars times what number would give us 80? 50 times what number will give us 80? Well, we know from years of algebra that to find that mystery number, we do the opposite of times by 50, which is divide by 50. And we get our mystery number. And that number is 1.6. So in other words, I'd go back in and I would replace all this with 1.6. And we could check our work. We could go back to the calculator and just check that 50 times 1.6 does indeed equal 80. So that looks good to go. And then we could check again. We could say, okay, well, does 80 times 1.6 equal 128? Because that would also have to be true for this to be the multiplier. So each output is multiplied by 1.6 to get the next output. And so 1.6 is our multiplier. Now that you have the starting value and the multiplier, take a moment, pause the video, write out your rule, and check back in to make sure your answer is correct. All right, so we get 50, again, that's the starting value, times 1.6, that's the multiplier, so we're multiplying by each time, to the x, where x is the number of years. Start with the starting value, multiplier, x is in the exponent. If I go over here to graph my function, put zeros here, 20, 40, 60, I'm going to change my scale so that I can actually fit some of these values. 0, 50, excuse me, 180, oops. To 128, it's about here. And pretty soon we are just about off the board. So the next one would be just up here. And we would connect these. Now we don't know what the context of this is, so we could go into the negatives if we wanted to. We don't have any of those values. So it would just be approximate. Oof, I'm having a hard time getting this to. All right, on this next page, this was the HP problem. We're given the graph and we're trying to find the rule from the graph. So first off, we'd have to actually fill in some of these values in our table. Looks like our starting value is 5. The next value, it looks like, would be 10. And it looks like at 2, it's 20. So let's see if we can figure this out. Okay, so again, 5 times what value is equal to 10 is the question we're trying to figure out. If I divide both sides by 5, I get that my mystery number, or my multiplier, is 2. And again, we can go back in and just check. We have one other value. And 10 times 2 is 20. So I'll go ahead and fill in the rest of my table. And this would be, let's see, 320. Given this table, you have the starting value, you have the multiplier, and you know it's an exponential equation since it's being multiplied by the same number each time. Take a moment, write your rule, pause the video, and we'll check in just a moment. And so y equals 5, the starting value, times 2, the multiplier, to the x. The last problem down here is about decay, percent decay. We know that a radioisotope is decaying at a rate of 18% every hour. Currently, there are 100 grams of the substance. How many grams remain after 6 hours? So again, let's just write out our general form. So this is the starting value, and this is the decay factor. We know our starting value is 100, so we can fill that in right off the bat. We just need to figure out what the decay factor is. Now, if something's decaying at a rate of 18% every hour, that means 18% is not there the next hour, which means we're left with a certain percent. And the way we figure out that certain percent is we take the 18% away from 100. So 18% is leaving the substance each hour, and that would leave us with 82% of the original substance. Now 82% can be converted into a number when we divide it by 100. And so this is our multiplier. This is what we're multiplying by each time. So now I go back into my equation and I can fill in my multiplier. I know that we're looking for the substance after 6 hours. Given that we have this equation, see if you can make the calculation to figure out how many grams remain after 6 hours. Pause the video and we'll check in a moment. So we plug in 6 for x, since that's the number of hours we're looking for. And I got 30.4 grams, so we have 30.4 grams of radioactive isotope after 6 hours remain. Let me add that to answer our question in a complete sentence.